Okay, so our last example where you need to think about and know how to do differentials in terms of approximations is something very similar to this table right here. I pulled from the AP exam. So they give you some select values of x, the function, the derivative, and the second derivative. And so we're still going to approximate some certain things, right? So approximating near values, using that tangent line. But then we also want to know, is this approximation an underestimate or an overestimate? So this is like a little bit of a new piece to this. And so first I would look at 1.7 and think about, okay, well, 1.7 is close to 2. So I'd think, okay, like let's at least know my x value is 2. And remember, the amount I deviate from 2, so is equal to negative 0.3. And to find the amount that y deviates, it's approximately the derivative at 2 times the amount of deviation, negative 0.3. And so then we think, okay, so what is the derivative at 2? So a couple more. So the derivative at 2, the derivative value is negative 3/2. So negative 3/2, and this is times negative 0.3. So negative 0.3 is negative 3/10. So that might make our calculation a bit easier. So we get 9/20. And, oops, I said it right, wrote it wrong. So 9/20, again, that's our dy. That's how much we're deviating from the y value. So then what was the value of f of 2? F of 2 was supposed to have been, f of 2 was 6. So we're deviating by 9/20. So then I could say that f of 1.7 would be approximately equal to f of 2 plus our amount of deviation, which we said was 9/20. And I've already forgot what it was. I think it's 6. Is that right? Short-term memory. Yes, excellent, 6. So we can say like 6 and 9/20. Okay. And then let's go ahead and get the other 2 as well, those approximations, just to have those down. You could work through them, and then you could check your work. So I would say, okay, 2.8. So x is really close to 3, a deviation of negative 0.2, again, because we're below. And so let's see, what was the derivative at 3? The derivative value at 3 is 4. So I would say, okay, let's kind of divide this up here. So our dy would approximately equal the derivative at 3 times our deviation. The derivative at 3 we said was 4. Our deviation is negative 0.2. So we get negative 0.8 as how much the y value deviates. The y value would be deviating from 8. This is what f of 3 is. So I could say f of, what was it, 2.8, I think? Yeah, f of 2.8 is approximately equal to f of 3 plus my deviation. And so that would be equal to 8 plus my deviation of negative 0.8, which was 7.2. And again, we'll determine if this is an underestimate or an overestimate in just a second. Let's go ahead and do one more. Let's go ahead and do that last example, 0.3. So 0.3 is closer to 0 than 1. And that's the thing, too. I probably should have preferences. I could use 1 as an approximation. I'm choosing, you're not going to get as close of a value as if you choose 0. So there, I'm picking the one that's closest. And if for some reason they gave me 0.5, which was like exactly in the middle, then I would choose one or the other to solve for that. Okay, so 0.3, we know the derivative value was negative 2 at 0. So I'm going to divide this out. So our x value is 0. Not that that matters. Our deviation now is positive 0.3 because we're above that value of 0. So my dy would approximately equal the derivative at 0 times my deviation. We said that, I want to say, actually I have no idea. I forget what the derivative of 0 is at 4? Oh, negative 2, there it is. So derivative is negative 2 times my deviation of 0.3, positive 0.3, so that's negative 0.6 is my dy. Negative 2 times 0.3, yes. And so, just to clean this up. Oh, good. Times, wow. Okay, so that's our deviation. Clean this up as well. Look at that. I'm sure it was probably fun. right? And now my OCD is getting the best of me. Okay, that's gonna be fine. So then f of 0 is equal to our value of, f of, wow, try this one more time. Super early in the morning. F of 0.3 is approximately equal to f of 0 plus my deviation. We said f of 0 was equal to -1 plus my deviation of -0.6. So we get -1.6. Okay, so now we have the three approximations. And the question is are they underestimates or overestimates? And it's all dependent actually on the value of the second derivatives. I mean, we have not used that yet, and there's a reason that they gave these to us, right? So think about what second derivatives measure. Second derivatives measure curvature, right? They measure is it concave up, concave down. And so if you are to analyze just a generic function, so like if I just graph a generic function over here, we'll go Husky color spirits, right? So like just graphing a generic function, and you look at a tangent line. Is that tangent line? And then maybe you look at this tangent line down here. Okay. So if you look at that tangent line, we know that the point of tangency and the function are identical at that point. But then as you start to move away, your approximation becomes a little bit farther from what the, like this tangent line comes farther away from the actual curve. But notice this, if this is curving up, right, if you're concave up, that means your tangent line will always be below the point of tangency. If you're curving up, the graph itself has a higher y value than your tangent line. No matter how steep of slope that is, it's always quote unquote underneath the function. And then in the exact opposite way, if you're a concave down curvature, concave down graph, your tangent line will always be above. And no matter what angle you put it, you're always going to be above that value. So by looking at concavity, we can determine is our approximation, right? We're using this tangent line, so is our approximation going to be underestimate or overestimate? So let's look at 1.7. We used 2. So at 2, we knew the second derivative was -1. So at 2, we were concave down. So again, thinking about something that's concave down. If you're concave down and you're using the tangent line, your approximation will always be above or an overestimate. So I can say that our approximation is an overestimate because f double prime of 2 is less than 0. In other words, it's concave down at x equals 2. So the curvature of the graph itself is always going to be wrapping below the point of tangency. And that's all you need. You need to state is an overestimate or an estimate, underestimate, and then you're just analyzing the second derivative. Second derivative is negative, it's concave down, therefore your value, and remember, your value is always on the tangent line, so that's how I know that's over what that value was. Okay? At 3, the second derivative is also negative, right? So at 3, we have still concave down, our tangent line's above, so we know it's an overestimate. Because f of x is concave down at that particular point at x equals 3. And that's, again, it's a simple, quick phrase that you just, you use to support your answer, but you just have to know it. And then at 0, we're concave up at 0. And so concave up at 0, and again, thinking about curvature, if you're concave up, your tangent line, no matter where you draw it, will always be below. So that would be an underestimate. And again, so the reason underestimate, because underestimate, and you could just say because f double prime of 0 is greater than 0, right? It's concave up, i.e. concave up, okay? And so, like I think that if you take a look at a problem like this, this idea of using an approximation, maybe using differentials to talk about error, talk about like underestimate, overestimate, those sort of piece together nicely in maybe like a free response type of question where there's a part A, part B, and part C, and maybe even a part D. Okay, so that's a lot, but that would be all of the notes for the differentials and the examples for this particular unit.